Okay, this is a complex section and it's going to take a while for you to think about. And we're going to talk about forces that repel and attract in molecules, and it's going to affect the shape of a molecule. And it takes a while to get used to this, it takes some practice. So this is something that's more of an intense section, bonding theories. So atomic and molecular orbitals. So atomic orbitals are the 1s2, 2s2, that type of thing. And then we can also talk about when electrons share in a cloud in covalent bondings, we get molecular orbitals. So when two atoms combine, the molecular orbital assumes their atomic orbitals overlap, and they produce an overall molecular orbital for the whole molecule. So atomic orbitals are those 1s2, 2s2, 2p things, and then they can combine together to make an overall molecular orbital for the whole molecule. So atomic orbital for an atom, molecular orbital for a whole molecule. And so when two electrons will bond together, they make a bonding orbital. So simple ones are sigma, when you have two orbitals bonding together. A simple one's in a sigma bond, so let's look at that. So when you have two S's that go together from two different atoms, here's one atom, here's another atom, they're going to bond together. They're going to overlap this part right here and that part right there and form a sigma. When two p orbitals, remember they're the dumbbell shape, when they overlap, they're going to look like this. And they're going to have a bonding part in the center. So this part here is going to overlap that part here, and there's going to be a lot of electron density right there. So that's a sigma bonding in p orbitals. Okay, pi bonds are when you have more than one overlap like that. So it's got the symbol pi, and we have bonding going on, and it's usually more. It's stronger because you've got this part right here coming together and you have this part here coming together, and it looks like this overall when it's done. So you have a lot of strength in that overlap on the top and the bottom. That's pi bonding. So after we know how things are bonding together, a single, double, and triple bond, we can look at something called Vesper theory, and this is important. So you need to take some time and think about this. It says that when atoms come together, they're going to have an overall shape for the molecule. So for example, methane has a carbon in the center, and then it's bonding with hydrogens in all four corners. So that makes a tetrahedral shape. And the angle between the carbon, the two hydrogens like this, the two bonds right here, is 109.5 degrees. So this is called tetrahedral angle, and this looks like a little tetrahedron. So there's different shapes we'll have to learn. So Vesper's theory says that all these hydrogens want to be as far apart from each other as possible. When they do that, it makes a particular shape. So this shape is tetrahedron. So those bonds try to stay away from each other as far apart as possible, and that makes a three-dimensional shape. So here's another example. This is ammonia, and we've got three hydrogens bonding here. They're separating as far as they can, but then we have that unshared pair of electrons, remember the lone pair? And it takes up space too. So instead of being a tetrahedron, this takes up space like a balloon, and this makes it a little bit different than the methane I just showed you. These have bond angles of 107 instead of 109. So when you have unshared pairs, they actually take up more room than the bonding. So this is actually pushing down further on these guys than in the tetrahedron. Just a little bit, 109 versus 107. So this is that methane again. And there's the ammonia. So these are the different shapes that we need to learn and understand how things are bonded together. And so we'll learn all these 9 shapes. Today I'm just introducing it to you, but we'll need to know these. So water looks like this. Anything that has 2 or 3 things in a row is linear. And this is that methane. Here's the ammonia. So these are important. So how is orbital hybridization useful in describing these? It gives information about the molecular bonding and the shape. So when they mix together the atomic orbitals, they form a hybrid orbital. And so, for example, if I have this happen, this is what's happening in methane. I've got carbons S and P orbitals actually combining together within one atom, hybridizing into some new shape, and turning into sp3 orbitals. So this is something new. And this happens quite a bit, especially in organic chemistry. When they come together, they look like that. So you have, you've changed carbon into this kind of four-legged shape, and then it's hooking to 4 hydrogens right there. So these are sigma bonds right here. End-to-end bonds are sigma bonds like that. We can also have double bonding, so it looks like this. You've got the end-to-end here, and then you have this overlap this away. So this is very, very strong. You've got sigma and pi bonding going on. And then you can even have triple bonds where you have sigma and then 2 sets of pi bonding going on. So this is called hybridization, where the middle atom is combining S's and P orbitals into new shapes of orbitals and then bonding using that. So let's try the quiz on this one. Oh, sorry, I went too fast. So molecular orbital belongs to the molecule as a whole. I just gave you the answer. And then look at Vesper theory. What do you think? So this is important, that everything tries to say as far apart as possible, and then it influences the shape of the molecule. And then orbital hybridization, this is the very end where I'm saying like S's and P's combine together and form new orbitals. And that's the answer for that one. So this is complicated. It's going to take us a while to get good at this, but this is just an introduction. So please read through the textbook on this. This is not an easy section. Okay, talk to you soon. I hope you learned a little bit. Talk to you later. Bye-bye.